Okay, so let's look at this question here, where we are saying, given that the relation R that maps X to X and a relation S that maps X to X are equivalence relations, determine whether the given statement is true or false. And then they're saying justify your answer. Okay, so these statements here, these two statements that I have here, are false statements. Okay, so these statements are false. But how are we going to justify our answer? So we need to show a counterexample. Okay, so let's do that. Let's do that. Okay, so we can say let my set X actually be 1, 2, and then 3. Okay, and then let's make an equivalence relation from this set here. So we can say my R, let me take my R as 1, 1, 2, 2, 3, 3, and then I have 2, 3, and then 3, 2. Okay, so let me take my relation R as this. Okay, so this relation here is an equivalence relation. So you can check it, but I've already checked it. It obeys all the three properties. And then let me take S as 1, 1. Okay, and then I have 1, 2, and then I have 2, 1, and then 2, 2, and then 3, 3. Okay, so you can also check that this relation here that I've given is actually an equivalence relation. So I have two equivalence relations here. So let's prove that their composition is actually not an equivalent relation. So what are we going to do? Okay, so we can start with the first one. So S of R. Okay, so how do we find compositions? We always start from the second the second relation there. Okay, so we'll go into the relation R and see what it does. So in R, I have one, R maps 1 to 1. Okay, what does the relation S do to that one? Okay, so if R maps 1 to 1, what does the S map the 1 to? Okay, so we can see that in this relation S, I have this 1 being mapped on 1, and then 1 being mapped on 2 here. Okay, so I'm going to write those as my first members of this relation. Okay, and then we go to 2. So 2, R maps 2 to 2. What does S do to 2? Okay, so S maps 2 to 1, and then 2 to 2 again. So I'm going to say 2, 1, and then 2 to 2 again. Okay, let's look at this one. So R maps 3 to 3. What does S do with 3? It also maps it to the 3. So we can see, so we can write 3, 3 here. Okay, and then comma. Let's look at this guy here. So 2 maps, R maps 2 to 3. And then what does the S do to the 3? It maps it to the 3. So it means I have the coordinate 2, 3, like that. Okay, so we are done with this. And then we check this. R maps 3 to 2. What does S do to the 2? Okay, what does S do to the 2? It maps it to the 1 and then maps it to the 2. So I have 3, 1, and then 3, 2. So let me write it here. So I have 3, 1, and then I have 3, 2. So this is our composition here, our S of what? R. This is my S of R here. Okay, so on this S of R, let's check the properties of equivalence relation. We know that an equivalence relation has to be reflexive, has to be symmetric, and it has to be transitive. Okay, so let's check the reflexivity there. So reflexivity, it means all the members of the set X should be mapped to themselves. Okay, so I can see 1, 1, 2, 2, then 3, 3. So we can say yes. Okay, S of R is actually what? Reflexive. Okay, so this property holds. And then let's look at the symmetric one. Okay, so symmetric, what can we see here? So symmetric, it means if I have 1, 2, I should have 2, 1. Okay, so 1, 2 is here. I also have 2, 1. 3, 2 is there. And then 3, 3, 2. I mean 2, 3 is there. 3, 3 is there. Okay, so these ones work. But let's look at this guy here. He's lonely now. Okay, so 3, 1 is here. So if this relation here, it has to be an equivalent, it has to be symmetric. Okay, then it means that we must have 1, 3 somewhere here. But we see that in this relation here, we don't have a 1, 3. So we can say no. Okay, not symmetric. Not symmetric. Okay, so we can state the reason there. Why is it not symmetric? Because 3, 1, okay, is a member of S of R, but the 1, 3 is not a member. Okay, you can say 1, 3 is not a member of this S of what? R. So it's not symmetric. So we have one property that does not hold. So it means that this relation here, okay, is not what? An equivalence relation, as simple as that. But anyway, for the sake of curiosity, let's check the transitivity there. So transitivity, we'll see that the transitivity on 1, 2 and 2, 3 there won't work. Okay, so if I have X, Y, and then Y, Z, okay, if that relation is to be transitive, then we must have X what, Z. So let's look at this guy here. I think, let me change the color here. Let me change the color to here. So if I look at this guy here, okay, the 1, 2, I also have a 2, 3. Okay, I also have a 2, 3, which is this guy here. Okay, so if I have 1, 2 and 2, 3, it means I should have 1, 3. But we see that in this relation here, we do not have a 1, 3. Okay, so we can say the transitivity there fails. So we can say no. Why? Because I have 1, 2 and 2, 3, which are members of the relation S of R, but 1, 3 is not there. 1, 3 is not a member of this S of R. So it means two properties here fail, the symmetric one and the transitivity one. Okay, so if you have any property failing, it means that this composition here is not an equivalence what relation. So we have proved that our claim where we said that that statement was false, it is true. Okay, it is true that that statement was false. All right, so we've proved that this guy here is not always an equivalence relation. Okay, so how do you prove the second one here? You do a similar thing. Okay, you can just say the set that was S, make it the set S, and then the set that was R, you make it the set S. Okay, and then you do the same thing that I did there, and then you see that the composition relation there, it won't have all the three properties of an equivalence relation. Okay, so that's that. Thank you so much for watching.